Next, I want to introduce the paper named Contrastive Domain Adaptation for Early Misinformation Detection, a case study on COVID-19. In this paper, despite recent progress in improving the performance of misinformation detection systems, classifying misinformation in an unseen domain remains an elusive challenge. To address this issue, a common approach is to introduce a domain critic and encourage domain environment input features. However, early misinformation often demonstrates both conditional and label shifts against existing misinformation data, for example, class imbalance and COVID-19 datasets, rendering such methods less effective for detecting early misinformation. Specifically, we leverage pseudo-labeling to generate high-confidence target examples for joint training with source data. We additionally design a label correction component to estimate and correct the label shifts, for example, class periods, between the source and target domains. And this is the setup. The data, source data, labeled source data from XX, target data, unlabeled target data from XT. Module. The classification module can be represented with function f. Objective. The objective is to adapt a classifier f trained on source distribution P to the target distribution Q. To adapt the trained classifier to the target domain, we propose CNNMD by approximating the target joint distribution. First, pseudo-labeling and label correction, where we perform pseudo-labeling and correct the label distribution QY in the target domain. And number 2, contrastive adaptation, in which we reduce intra-class discrepancy and enlarge inter-class discrepancy among examples from both domains. By leveraging pseudo-labels from the first stage, we estimate and minimize the discrepancy between conditional distributions Pxy and Qxy. Given access to labeled source data access, we first pretend the misinformation classification system. In sum, the pseudo-labeling and label correction stage via the label correction component can be formulated as this. After label correction, we filter the pseudo-labels to select a subset of the target examples for contrastive adaptation. Based on the combination of intra-class and inter-class discrepancy, the misinformation detection system F learns a future representation that separates the input from different classes and confuses input from the same class. Then we'll compute the contrastive adaptation loss to reduce the intra-class discrepancy and enlarge the inter-class discrepancy. For each input, the optimization process is described in the algorithm 1. This is the experimental design. Datasets. Adopt 5 source datasets resourced before the COVID outbreak and 3 COVID misinformation datasets to validate the pros CNND. Module. Use row BRTA as the information detection module to perform the proposed CNMD. Baselines. Select 2 state-of-the-art baselines, DAAT and EADA. We first present the supervised training results of all datasets in Table 2. The evaluation results on the target datasets provide an upper bound for the adaptation performance. We observe the following. First, the performance varies for different data types. For example, row BRTA does not perform well when we train on claims without additional knowledge. Number 2, for disproportionate label distributions, balanced accuracy, BA better reflects the classification performed by weighting both classification equality. For example, the classification accuracy is 0.9587 on getting real, while the BA score drops drastically to 0.8459. This is because the dataset contains overwhelming true examples and by only predicting one class, the module still achieves over 0.9 accuracy. And this is the qualitative analysis. Contrastive is widely used COVID or misinformation datasets. We thus performed experiments with DAT, EADA, and CANMD using constraints as the target datasets. Valid examples are in orange, while misinformation samples are in green. For source datasets, we denote the favor with F, getting real with GR, gossip cop with GC, Lear with L, and Femic with P. This is the Adaptation studies. Label correction and constructive adaptation. We evaluate the effectiveness of the label correction component and constructive adaptive by comparing our results from CAMAD to the results training without label correction and constructive adaptation. This is the result. Unlike existing methods, we design a label correction component and adapt the conditional distributions to improve the target domain performance. Extensive experiments demonstrate that CAMD is effective in domain adaptation for misinformation detection by achieving 11.5% on average improvements and up to 34.5% improvements under label shifts between the source and target domains. Thank you.